I'm Jay from University of Utah, and so as Angela mentioned that today, I'm going to share about like how, microfluidics is revolutionizing both astrobiology research and astronaut health monitoring. And here's an overview of my lab activity, and my lab works on the three main research topic, which are microfabricated instrument, development for the space research, and organ chip for ocular renal system, and bioelectronics for the digital health. And as you see that, it's, coverage is quite wide, but it's somewhat related with that. And I'm mostly focused on, the space instrumentation development today, since we're in the short time. And I love to discuss about the other topic another time. And so let's dive in. And as you know, the life requires three fundamental components: water, energy, and molecular building blocks. So water serves as a life, universal solvent and enabling nutrient delivery and waste removal while supporting the biological processes. The building blocks, primarily the organic compound, and form the foundation of life structure. On Earth, amino acids are essential building block, serving as a basis for the protein and cellular components. Finally, life needs an energy, whether from sunlight or geothermal activity, to drive the biochemical reaction that sustain the living system. Wherever we find those three elements together, and we can, find the potential for the life. And what happened when the water exists, but it's really cold? And NASA found some interesting moon near the planet that are made of ice, called ocean world. So, as you see this many ocean world, we can, see that. But among these, particularly three moons are, very interesting to the scientists, Europa, Titan, and Enceladus. So Enceladus is one of the Saturn's moon, has emerged as a prime target for the astrobiology research. And the Cassini mission, provide the groundbreaking discovery about the Enceladus, notably its active ice plum eruption from the surface, as you see that on the south pole of the Enceladus. These plums suggest that the presence of a subsurface ocean, but a key question remains: what maintained this liquid water? So the answer lies in tidal heating. The Saturn's immersed gravitational force create the internal friction, so within the Enceladus, through the constant stretch and compression. So this mechanism provide the energy needed, to maintain liquid water beneath the ice surface. Now we know the Enceladus has water energy. How about the building blocks? We have to find out for the future mission. We don't know yet. So now, how can we determine between abiotic or biotic process through the molecular analysis? On the left, we observed the racemic distribution. This pattern emerged from the random chemical reaction in nature, where both left-handed and right-handed molecule form equally without preference. The right graph show the homochiral selection, which is characteristic of a biological system. And these distinctive peaks, as you see here, illustrate how living organisms selectively, utilize the molecule with a specific handedness. So on Earth, life predominantly create and employ the left-handed amino acids, establishing a homochiral system. This tendency toward the homochirality serve as one of our key biosignature. For example, like Earth and living organism exclusively use the just 20 specific amino acid among the numerous the possibility. The meteorite and asteroid sample provide the evidence of this phenomenon as well. And so Murchison meteorite provide our first significant insight. Analysis revealed the substantial concentration of the organic compounds, aromatic hydrocarbon, and over 15 distinct amino acids, including the evidence of heterochirality with some ambiguity. Typically, like Earth contamination remained, one of the concern, limiting our ability to draw definitive conclusion. So most recently, as you see on the right panel, like NASA's OSIRIS-REx mission has provided a breakthrough by collecting pristine sample from the asteroid Bennu. This uncontaminated material has revealed remarkable finding: all 5 nucleobases essential for the DNA, RNA formation along with 14 out of 20 amino acids necessary for life. Importantly, amino acids show the heterochirality, suggesting an abiotic origin. So the pristine sample analysis represent the significant advance of our understanding of prebiotic chemistry. So, since sake of time, I cannot explain more, but hopefully you guys can find this paper on the below and read. This is super interesting paper that you can find phenomenal scientific finding. So then while sample return missions like OSIRIS-REx have been invaluable, maintaining the sample pristinity during the collection, return, and analysis, presents the significant challenges. This is why in situ analysis often provide the best strategy for minimizing cross-contamination and ensure the most reliable results. So I just pulled this, figure showing how far, from here. So then this image showed the Earth as a mere dot in the space, emphasizing the vast distance and constraint we face in extraterrestrial analysis. For successful in situ analysis at these distance, our instrumentation must meet the several critical requirements. So the core instrument demands are straightforward yet challenging. The system must be compact and miniaturized, operate within the minimal energy consumption, meet the rigorous space certification standard, and function autonomously without human intervention. So chemical analysis specification pose the further emerging challenges. We need system capable of processing extremely small volume and performing the rapid analysis, maintain the high detection sensitivity, and simplify all the chemical procedure. So this is precisely where microfabricated bioanalysis system become particularly valuable. And these systems satisfy these requirements through their miniaturized nature and efficient operation and the precise analytical capability. So let's go back to one of the history. The URAY instrument is developed for the European Space Agency ExoMars mission. Was designed to detect the molecular building block and evaluate their biological origin on Mars. This URAY employed a microcapillary electrophoresis device for its exceptional sensitivity, capable of detecting compound at the picomolar level. And then instrument processed Martian soil sample, through the multiple key steps. Like the first step is typically like the sample prep step with a subcritical water, and to dissolve all the organic compound in a certain temperature. And then extracted compound then moved to the microcapillary electrophoresis device to get the trace of organic compound. But, so due to the multiple political agent, issue, then URAY, kind of halt now. But then let's go back to the microcapillary electrophoresis theory, and then we can go further down. So microcapillary electrophoresis achieved the molecular separation through two main mechanisms: the electroosmotic flow and the electrophoric flow, as shown in the diagram. And the molecules are separated by size and their charge. With through the small capillary device, enable their separation. And to implement the capillary electrophoresis in the microchannel, as you see, the labeled sample are injected through the a channel under the bias voltage, and by switching the voltage polarity, and the small sample plug travels through the long channel and detecting the target molecules. However, CE require a significant sample processing step to label each chemical compound in the liquid sample before highly sensitive analysis. So this labeling chemistry required the metering, mixing, the reacting with a precise volume control. So to utilize the CE properly for a space exploration mission, then extensive automated sample processing is essential for precise and accurate handling of the small sample volume. So the breakthrough came in the 2012 through our collaboration with the Mathis group at UC Berkeley, where we developed the lifting gate microvalve technology, enabling the wafer scale integration. So by connecting the multiple valve at the same time, and we can manipulate the small volume of the fluid precisely and accurately. As you see here, the vacuum and the pressure just like the switching back and forth, then we can deliver the sample to proper destination. So with this lifting gate microvalve technique, and we fabricate the two-dimensional microvalve array to create the programmable fluidic processor. The valves in this array act as the about 140 nanometer reaction chamber, and the bolus of the fluid can be discretely transferred between the valves. In this array, we can generate any fluidic path from any outlet, any inlet to any outlet. Using this programmable microfluidic processor, we could perform all the basic the fluidic operations, such as metering and mixing, washing, reacting, and combining them all to achieve totally automated, bioanalytical assay. As you see here, the demonstrated video, just use the 4x4 the array to mix the 4 different solutions. So then this is one of the demonstrations. So then by using the just changing the program, then we can create the multiple programming for the fluidic manipulation. So this fluidic processor was integrated with a CE system for autonomous CE analysis. This image shows our actual device, wafer scale integration. Then compact design represent the significant advancement toward the automated chemical analysis for space exploration. So all labeling chemistry are done using this rectilinear microvalve array by incorporating various essential components such as labeling reagent like Cascade Blue and Pacific Blue, washing buffer, and separation channel for the labeled carboxylic acid, amino acid aldehyde ketone. Then the first labeling, carboxylic acid, we use EDC chemistry to label with Cascade Blue, and for amino acids, we use NHS ester the chemistry to label amino acids with the Pacific Blue. For the aldehyde ketone, the Cascade Blue was used through the hydrogen chemistry. So once all labeling processes were done, and then labeled sample were transferred to the sample inlet of the CE chip. So the integrated approach dramatically improves the previous system by enabling concurrent processing of different chemical species while maintaining the small footprint essential for the space application. So then this video showed what I explained before. After this process, we got the electropherogram. As you see in the right panel, and the blue trace at the top represent the amino acids, where we clearly identify the 4 distinct amino acids along with Pacific Blue. And the purple trace on the one below and show the carboxylic acid marked by the presence of EDC acetic acid and formic acid peaks labeled using Cascade Blue. And the green trace represent aldehyde ketone compound showing distinct peak for the acetone and formaldehyde. And the one on the last, the red trace, show the combining all this analysis in the single run and demonstrate all systems capability to simultaneously detect the separate the multiple component compound classes. All peaks are well resolved with the minimal overlap, and in case we see the overlap, then we can go back to the individual run as well. That's how we compensate it. So these comprehensive separation capabilities highlight the efficiency and versatility of our integrated microfluidic system for chemical analysis. However, there's still a manual step required for the initial step and buffer loading, etc. For the fully automated separation, and these manual steps have been integrated into the programmable microfluidic platform. So to overcome limitation again that I mentioned previous slide, and we enhanced our programmable microfluidic platform by integrating all required sample, reagent, and buffer storage while preserving the core programmable microfluidic platform technology called Microfabricated Organic Analyzer for Biosignatures. So go by MOAB. So I'm pretty sure you've heard MOAB in Utah. So that's one of my favorite location typically for the vacation. So this comprehensive system integrates all essential components like a pneumatic controller for the precise fluidic manipulation and the manifold system for integrated laser-induced fluorescence detector and capillary electrophoresis interface for the high-resolution separation. So this transformation from the basic microfluidic chip to a complete analytical platform marks a crucial advancement toward the deployable instrument for the space exploration. So as shown in the schematic on the right side, and this three-layer stack architecture effectively organize all the necessary components while maintaining the compact form factors. In detail, the chip incorporate 53 interfacing ports, including 4 the fluidic inlets and 39 pneumatic ports and 8 detection ports. And the comprehensive support system enabled the complete fluidic handling and analysis capability. And the system utilized the 63 microvalves with a 2 to the 39 potential state, which is like the enormous number of possibility for the routing of all the fluidic paths, and a centered around 3x4 valve array microfluidic processor on the center. So then, integration of 32, sample storage well and 2 capillary electrophorese channel makes this a truly self-contained analytical the platform. So with this fabricated chip and the pumping capability of this platform was evaluated, and so our evaluations show the linear relationship between the number of pumping valve and dispensed volume per cycle with high precision. So when we got is like coefficient of variation is less than 4%. So furthermore, we found that the dispensed volume correlates with the effective fluidic length. So this characterization enabled precise volume control. So we can calculate exact dispensed volume by multiplying the volume per cycle, volume for valve determined by the path lengths, and number of valves used and number of cycles. So then we can, accurately calculate how much volume we transfer to certain wells. So this video show a 2-part mixing operation. So typically this is like empty. So if you put the like a space, this is like the fully empty. So then we have to prime this chip before we use it. So then this yellow dye is like one of the prime step. And after prime, and then we pull the like 2 different color pull in from the reservoir storage well. So then we can see like how well they operate those. So then especially this one is for the layering mix. So then we can pull the red and pull as green sequentially. So then we can mix well. So, and then with this after this characterization and this we create the actual MOAB system as you see on the picture. So the MOAB is only 2 kilogram total mass with a 3-liter volume. So using the MOAB, then we performed the fully automated CSC analysis following this analytical workflow, and the buffer loading for the system preparation and the labeling of target compound and sample loading into the separation channel and the measurement through the capillary electrophoresis and washing step for the next use. So then, as you see, the electrophoregram showed the separation and detection of multiple amino acids from the manual run and the MOAB run. The high resolution separation is evident from the distinct peak, and with each representing different amino acids such as beta-alanine and glycine and others. Then overlapping red and blue trace demonstrate the reproducibility of our analysis, showing consistent peak position and intensity. And this fully automated operation combined with high quality separation results and demonstrate MOAB's capability as self-contained an analytical platform suitable for the autonomous chemical analysis. With this MOAB, and we performed the engineering evaluation for showing robustness of this system. And so before that, we have to check how this chip survive, how long. And then this left graph demonstrate the valve durability through the repeated actuation, testing from 6 to 10,000 cycle over 18-hour period. So remarkably, consistent flow rate profile across all actuation cycle demonstrate our the microvalve array chip's reliability, and dispense volume per cycle shown in the red and remains stable at approximately 500 nanoliter throughout the testing period. So the right graph, show the long-term stability testing over 3 years, including exposure to the kind of simulated launch conditions. So then, so we're going to discuss a little bit later. And then flow profile, as you see, the maintain consistency from the fabrication through the 2 year and 2.5 and 3 years of aging, with a stable volume dispensing around 500 nanometers per cycle. So, after this reliability test, and then we're kind of confident that we can utilize for the long-term the space exploration. So, in addition to our ground test, and we conducted a crucial microgravity test in partnership with the Zero-G cooperation. So then Zero-G aircraft, as you see on the blue panel, and achieved microgravity through a parabolic maneuver. And they start at the 34,000 feet, and it descends at 45 degree, creating 1.8 G, and then arc to the produce about 30-second zero gravity status. And the maneuver ends with 1.5 G again, ascent before leveling at the 24,000 feet. Then we test MOAB extensively during the 30 parabolic cycle across 5 separate flights. During each cycle, then we systematically evaluate all critical function, pumping operation, fluid mixing, and the chemical analysis, and the capillary electrophoresis separation throughout the various gravitational conditions. And photographs show here, and the movie as well, were captured during one of our early parabolic flight by specialized microgravity photographer. He's amazing. I mean, it's no sickness at all. The maximum number of cycles that I could handle was like 25. And after 25, you see my face still smile, because this is early stage. But after 25, and I just lay down like, hey, move up and down. That's all I did. But my awesome former graduate student, Zach, managed these gravitational conditions well enough to perform all the required experiments. So during this microgravity test, and we evaluate the flow characteristics across 4 distinct gravitational environments: hypergravity, Earth gravity, and the Martian and the lunar gravity. So the left figure show the flow rate profile during the microvalve operation cycle during these various gravitational conditions, as predicted by the simplified Stokes equation, which govern micro scale fluid behavior, and gravity has a minimal impact on our microfluid operation. And overlapping flow profile across all gravity conditions demonstrate this independence. This is the key advantage of microfluidic system, where surface force dominate over gravitational effects. And the normalized flow rate, shown in the right, graph, further confirm this behavior. Note that is under hypergravity condition, and we observed the approximately 95% of Earth gravity flow rate, and a slightly reduction attributed to the aircraft flight angle during the parabolic maneuver. So they don't disclose what angle they kind of maneuver when they go up and down. So that's why it's kind of like the unknown factor. So that caused the little bit of off. But overall, this result validate our theoretical prediction and confirm MOAB's capability to function consistently across the range of the gravitational condition it might encounter in various exploratory exploration mission. So, and we also performed the CE under the various gravitational condition. The plot shows the 2 critical data set, and a ground control analysis, as you see the black trace, and in-flight analysis, as indicated the red trace, with the blue line tracking the G-force variation during the flight. During the parabolic the maneuver, and we observed the G-forces transitioning from 0 to 1.7 G. So the remarkable consistency in separation profile shows the identical amino acid peaks, between the ground and in-flight condition. So this validates our CE separation method robustness under various gravitational conditions. The maintenance of separation efficiency under these varying G-force further validates our system's readiness for the space application, where gravitational condition may kind of fluctuate. So, and as I mentioned previously, our target is Enceladus, so the ocean world with the active ice plum. So we would capture plum particle and resuspend them and analyze their organic compounds using the MOAB. The capture phase use around about like 100 square centimeter collector that captures ice particle with around 40% efficiency, and collecting about 20 nanoliters of ice per pass, which means if we do mission, then explorers should like to capture multiple times. So then we get the enough volume and concentration that we can analyze it. So we concentrate this into 25 microliters of solution for analysis. So in the labeling phase, and our microfluid processor automatically mix sample with buffer and labeling reagent at the certain dilution factors, and then analysis detection stage combine capillary electrophoresis with the fluorescence detection system, achieving sensitivity around the 75 picomolar for the amine and amino acids. So this integrated system let us analyze the potential biosignature in the Enceladus plum from the capture to detection. So this animation visualize our dream of Enceladus flyby. So each frame represents years of engineering, scientific preparation, showing our spacecraft would dance through the ice plum of this ocean world, Enceladus. So from concept to the future reality, I mean, this mission could unlock the secret of a potential life on the Enceladus. So I like this one, this word from Carl Sagan. I don't want to know. I don't want to believe. I want to know. That's a kind of intriguing, the statement for our work. So then, one of the tests that we did is that so we test impact at the 3 velocity. So then to understand how we can capture with a certain velocity. So then, 1.1, 2, and almost 3 kilometers per second. The matching is expected spacecraft encounter with the Enceladus plum. So here you see the impact crater on the top, and the fluorescence image is showing on the bottom panel. So for the particles between 7 to 70 microns, we achieve capture rate up to about 30% at the velocity of the 1 to 3 kilometers per second. It's like really hypervelocity. And the small particle show the better capture efficiency, of course, and then about 23%, and then 4 to 5% of the about 25, 35 micron particle. So the fluorescence confirmed the organic survival during the high velocity impact, validate our collection strategy. These findings directly inform our capture system designed for the future Enceladus plum sampling missions. So we're working on it, like how we're going to improve those capture efficiency. So yeah, so this is kind of like related with the astrobiology work, but then this MOAB can also adapt for the monitoring the astronaut health during the space mission. So astronauts face multiple physiological challenges in space, as illustrated here. The radiation exposed, and the space-associated neuroocular syndrome, and the muscle degradation, and the renal dysfunction and bone degradation. Those are the kind of representative of the health concern. So these conditions need continuous monitoring through the metabolite analysis. Our MOAB can be reconfigured for the multiplexing metabolite assay. So then, as you see, our platform integrates the multiple, the assay capability as shown in the left schematic, including calcium and peroxide and creatinine detection channels with the dedicated reaction zone. And this movie shows the sequence of the multiplexing metabolite assay with a sample and reagent. And the first performed the detailed calibration study for the multiple metabolite individually, and then confirmed the linear response. The range is for the calcium up to 300 the micromolar, hydrogen peroxide is up to 1 micromolar, and creatinine is about 20 micromolar. So we also confirmed the mixture of sample to validate multiplexing and metabolite test. And then we evaluate this multiplexing test performance during the parabolic flight, testing again. So the center graph show our operational sequence, the reaction, initialization, and incubation, and the detection phase under various G-force. So the most of case of calcium hydrogen peroxide assays show the similar results between the flight and ground testing results. So during our final calcium assay, we kind of intentionally introduced a valve malfunction to test system resilience. So this results in the altered dilution factors and visible in the elevated flight calcium measurement compared to the ground control. So this test achieved the, it's kind of debating now, but our observation and then the evaluation is close to in between TRL 5 and 6, and then confirming our platform readiness for the automated health monitoring and the various gravitational conditions. So this dual use capability makes our technology particularly valuable for the future space exploration. So then that's closing. We have successfully demonstrated the MOAB as a fully automated multiplex analytical platform. So the system's key strength, lie in high programmability through our microvalve array technology and the precise organic compound separation detection capability, and the process toward the TRL the 5 to 6 qualification validated through the extensive vibration and microgravity test. By the way, I didn't show all the vibe tests, but we've done and then passed all the the test. So look ahead. So we're advancing several exciting developments, such as the capture plate development, and also we kind of try to embed some of the sensors so that we know like the valve actuation status. So these development represent not only technological advancement but opportunity for the broader microfluidic community. So I'd like to conclude with invitation to the microTASC community. Space exploration present the huge challenges in analytical chemistry and bioanalysis. So your expertise and innovation can play a crucial role in advancing this technology for the future mission. So I'd like to express my sincere gratitude to many individuals who made this work possible. First, I want to acknowledge my dedicated students and postdoc, and with a special thanks to the Dr. Zach Aslak, my former grad student at the University of Utah, and Dr. Metin Golozar, who worked with the team at the UC Berkeley, and their tireless effort and innovative thinking were instrumental to this project success. So this work wouldn't have been possible without our outstanding collaborator at the UC Berkeley Space Science Lab. I particularly want to thank to Anna, Jeremy, and Rich for their expertise and contribution. Finally, I want to acknowledge NASA for their financial support through the multiple grant and which enabled this research. Thank you all for your attention.